Good afternoon. My name is Synne Wesmann, and I'm an equity analyst here at Pareto Securities. Today, I will cover the carbon capture market. Carbon capture has re-emerged as a key technology in decarbonization efforts. Today, we will cover the problem we are facing, why carbon capture can provide a solution, how the market has developed the past decades, and importantly, how to accelerate the deployments in the decade ahead. First, as mentioned several times today, time is running out. Following a dip in emissions last year, emissions are now trending back to pre-pandemic levels. And the world is changing. The pace of renewable installations is accelerating every year, and investments towards the energy transition are fast increasing. Still, we are not doing enough. In the IEA's stated policy scenario, which covers the current regulations, global emissions would increase towards 36 gigatons in 2030 and remain at this level throughout the next 2 decades. Ambitions are increasing, but if we include the plans announced to date, this would only reduce emissions by roughly a third by mid-century. In other words, far from the net zero needed for keeping the rise in global temperature below 2 degrees. Assuming that we switched all electricity to renewables or green power tomorrow, we would still not reach net zero by 2050. This is mainly due to the hard-to-abate sectors, which are inherently difficult to decarbonize. These include cement, steel and iron production, chemicals, and also heavy transport. For instance, every ton of cement produced emits an average of 0.6 tons of CO2. The majority of these emissions are process emissions. So while innovative production methods and technologies could be able to reduce some of it, carbon capture remains one of the few and most cost-effective alternatives for these industries. In a net zero scenario of IEA, CCS will on average cover about 70% of the production methods by 2050, up from practically zero today. This naturally translates into an immense need for carbon capture facilities, equal to about 2,500 million tons by 2050, or roughly 6,400 Northern facilities. It is estimated that carbon capture solutions represent about 9% of the emission reductions needed by 2040. This covers the CCS impact in a number of different applications. However, there are 4 key areas where carbon capture will make a difference. This includes the mentioned hard-to-abate sectors, and especially steel and cement, which together represent about 15% of global emissions. In addition, hydrogen is emerging as a key fuel to decarbonize other industry and heavy transport. However, at the current cost level of green hydrogen, blue hydrogen will be a key transition technology to kick off the hydrogen economy. Another aspect which will be of particular importance in emerging economies is the fact that there is a large and growing fleet of fossil-fueled power stations, and the majority of these have operating lives well beyond 2050. Retrofitting these plants with carbon capture will be one of the few alternatives to shutting them down. Lastly, we will not reach net zero across all industries and sectors. Therefore, technologies that net reduce the amount of CO2 in the atmosphere will be key. This includes bioenergy with carbon capture, but also direct air capture, a technology that today is very costly, but will play an important role in the net zero budget. Carbon capture is, of course, nothing new. It's been around for decades. The first facility became operational in the late 1960s, and we installed the first offshore carbon capture plant here in Norway in the 1990s. However, market deployment has been slow, and today's capacity only covers the emissions of Norway, which again only translates to about 0.1% of global emissions. If we view this number relative to the required amount of CO2 captured in order to reach net zero, I think you will understand the challenge ahead. The capacity would need to grow about 40 times towards 2030 and capture roughly about the same amount that Russia emits every year. This would again need to double by 2040, capturing somewhat less than Russia and Europe combined. Going towards 2050, we would need to double capacity again, effectively eliminating the combined emissions of both Europe and the US. So, in other words, to have a fighting chance, the rate of CCS deployment would need to accelerate materially the coming decade. Roughly speaking, there are some key drivers for this development. First, the market will need government funding and support in order to grow. These are large investments, and if the business case is not there, corporations will need incentives to invest. Several governments have already announced plans and funding of projects. In Europe, the EU Innovation Fund is set to distribute its first grants this coming November, and the UK, Norway, and the Netherlands are all allocating funds to the development of hubs and shared infrastructure. In the US, the Department of Energy has allocated funds to CCS R&D over several years. However, in the recently proposed infrastructure package, this includes about $2.5 billion in storage projects and another $3.5 billion to the development of direct air capture hubs. Also, progress in the regulation supporting a key incentive for the companies, namely the carbon price, have evolved materially. The EU Commission issued its proposed legislation this summer, where it tightens the ETS market and include additional sectors in the ETS scheme. This has resulted in increased expectations of higher carbon prices in the future, with the BNF now estimating a price of above €100 by the end of the decade. Compared to where the Norwegian and Dutch governments have outlined where their national carbon taxes will be by 2030, this seems reasonable. However, the need for government subsidies and funding to spur deployment is of course nothing new and very similar to what we've seen within other renewables such as solar and wind. For illustrations, let's do a much too simplified but effective calculation. In 2014, the UK government issued the first contracts for difference for offshore wind projects. The Burber Bank extension project was awarded a subsidy of £150 per megawatt hour, in theory, then eliminating gas or fossil fuels for 230,000 households. On average, the annual CO2 emissions for power generation per household in the UK is about 0.6 tons of CO2. The Burber Bank project therefore eliminates about 0.16 tons per megawatt hour produced, or 140,000 tons per year. In other words, the UK government implicitly paid about £940 per tonne of CO2 avoided, equal to about €1,100. Of course, compared to the current carbon price of €60 per tonne, this figure is extreme, and it simplifies the big picture and should be seen in light with the leading position UK has taken in the offshore wind industry. However, it shows the role the government plays and the commitments needed to build the industries of tomorrow. And another important element for increasing deployment of CCS is, of course, the clients. The past 5 years, we've seen the number of companies with science-based emission targets double every year. Further, about a fifth of the largest corporations in the world has committed to net zero, including some of the largest cement and steel manufacturers. Net zero targets and concrete plans for reducing emissions will, for many countries and companies, include carbon capture. This can be seen in a number of project announcements. Just considering the past 20 months, the number of announcements has actually outpaced the number of announcements in the 10 previous years. So the pace is definitely picking up. However, we need new technologies as well. As mentioned earlier, we will not reach net zero, and net negative technologies like direct air capture will be a key part of the decarbonization efforts. Climeworks started production at the Aker facility last week, the largest direct air capture facility to date, capturing about 4,000 tons of CO2 every year. This is, of course, only a per mil of the global capture capacity today and minuscule seen in relation to global emissions. However, DAC will play a key role, and the IEA estimates that we need more than 160,000 orcas by 2050 if we are to reach net zero. There are a number of different technologies currently under development, and some of these will move from the pilot to more commercial applications the coming years. And they all have a target of reducing the capture cost materially, because costs are currently too high. The capture cost will vary from facility to facility and depends, amongst other things, on the concentration of CO2 in the flue gas. The lower the concentration, the higher the cost. However, we can see that at the current carbon price of 60 euros per ton, the picture is quite different than when we were at 30 euros per ton only a year ago. Aker Carbon Capture has outlined an ambition to reduce costs by 50% by 2025. Based on the estimated cost at Norcem from 60 to 100 euros per ton, depending on the discount rate, this would translate to about 30 to 50 euros by the mid-decade. Another key aspect of the cost is, of course, transport and storage. A key focus point in Europe has been the development of hubs, with about 13 hubs currently under development, equal to about 30 to 50 million tons of storage capacity. And this has a meaningful impact on costs. Considering the Northern Lights project, the first phase will store 1.5 million tons per year. Increasing this to 5 million tons in the second phase, the project cost will increase about 20%, but reduce the cost per ton by 65%, which naturally has a positive impact from the different companies evaluating carbon capture projects. And finally, increased deployments will spur more projects as technology improves, costs come down, and client interest drive more investments. We have seen a meaningful uptick in announcement and also projects under development the past years. However, considering the current pipeline, this equals about 200 million tons by 2030. This is a bit more than a tenth of the required capacity if we are to have a fighting chance for reaching net zero by 2050. So, as the market dynamics and drivers are seemingly all coming together, what can stop us now? Well, two key elements. First, there is opposition to CCS. The first is from environmental groups who argue that carbon capture is just a tool to extend the lifetime of fossil fuels. However, the key application for CCS has increasingly moved from power to more industrial and hydrogen applications. As mentioned, carbon capture will have a role to play in decarbonizing power plants in emerging countries, but in advanced economies, the focus will primarily be on hard-to-abate sectors. Second, there are concerns about the safety of storage facilities, especially onshore. However, based on operational data from the plants that have operated the past decades, these fears seem unwarranted, and improved information on this is needed to prevent the trend of NIMBYism. Lastly, in the past, the time from announcement to commissioning of the plants have taken about 4 to 8 years. And the trend has been that the larger the project, the longer the development time. However, as the regulatory framework and funding improves, together with increased pressure to decarbonize, we expect projects to become operational within a 2 to 4 year timeframe. Overall, we are running out of time. The IPCC report was a brutal wake-up call for countries and corporations alike. If we are to keep global warming below 2 degrees, we will need to halve emissions within the next 10 to 15 years. However, the upcoming COP26 in Glasgow provides the needed arena for action. Here, governments from around the world are expected to both commit to net zero, but also outline much more ambitious plans on how to reduce emissions by 2030. We expect carbon capture to be a key part of these strategies and continue to expect CCS to play an important role in the decarbonization efforts the next decade.